Hey everyone, I'm Anshuman from UVA, and today I'll talk about a research on distribution inference risks with my advisor David Evans. And right before we get started, I'd like to show you a figure that captures the essence of our work. What you see on the x-axis here is alpha, and that's essentially the probability of a particular attribute being true for any given sample that you take from the training distribution of a given machine learning model. And on the y-axis is the mean square error of an adversary that looks at the same model and then tries to predict this alpha. So let's say you have face images, then the alpha for your specific scenario could be, let's say, the probability of that person being a female. And this is what we'll vary in these experiments. And this quantity here, n leaked, is a measure to look at the given model and setting and try to quantify how much leakage there is. And what we see is across all the datasets that we looked at, the leakage is quite non-trivial. And that's what most of the work is about. As part of our work, we propose a general definition for distribution inference that allows us to come up with a metric that helps measure the amount of leakage in these cases. We also propose 2 new black box attacks and perform systematic evaluation of risk across different properties and datasets, and that's what I'll be focusing on in today's talk. Let's say you have some sort of distribution of data from which you sample some dataset D. The general pipeline in any such computation is you perform computation on the given dataset and that generates an output. So if you were to draw a parallel with machine learning, the distribution would be the underlying training distribution, the dataset would be the training dataset, and then the computation is training a machine learning model which generates the machine learning model in the output itself. The most well-studied level of inference risk granularity is dataset inference, and the most popular example perhaps is membership inference, where you're given a machine learning model and you're trying to infer whether a particular point was part of the training dataset or not. And there's tons of work in both in terms of attacks, defenses, as well as theoretical contributions. Now, coming over to the distribution level, things get slightly different because the adversary no longer cares about the particular dataset, but the underlying distribution from which that dataset was sampled. So let's say the adversary looks at the machine learning model and wants to infer whether the underlying distribution had, let's say, more green samples than red samples. And that is clearly a property of the distribution because there are multiple possible data sets from the distribution that would satisfy the same property and yet would output obviously different datasets and consequently different machine learning models. We set this up as a cryptographic game inspired by Yom et al.'s work. We start off with this underlying natural distribution D, which is assumed to be public, and then we have these 2 distribution transformation functions, G0 and G1. As a concrete example, let's assume D is the distribution of face images available on the internet. G0 could be something that creates a distribution from this distribution such that the probability of sampling a female or not a female is equally likely, whereas G1 is something that results in the probability of sampling a female as twice as likely as male, let's say. Then what the victim does, like any standard cryptographic game, is samples a random number between 0 and 1, so it's either 0 or 1, and based on that number, it picks a training dataset from the underlying training distributions and trains a machine learning model M on it. And then the adversary's task is to look at the model itself along with whatever public information it has and try to predict which of these 2 training distributions the model's training data came from. And this is very different from a kind of inference risk that looks at the dataset level because this is no longer a property of the particular dataset. The adversary is not interested in this part of the whole setup, it's interested in this part of the setup. So it really cares about the distributions and the properties, not the exact dataset. And of course, even though the adversary has access to the victim's model, there's different levels of access. So the black box access assumes standard public information, that is the distributions and the transformation functions itself, as well as API access to the victim model. So it has access to the victim model and whatever confidence values the victim model generates for any given data. And for the white box setting, the adversary has, of course, full access to the victim model that includes the parameters, architectures, and all of that. Now I'll describe one of the black box attacks that we proposed in our work. Now this is a very straightforward test and which we call the loss test, and the way this works is the adversary starts with these two distributions, which it anyway has public access to, and it samples some data from both of these distributions. And then let's say it has a given victim model. It'll perform inference on the first set of data and take note of the accuracy it observes, and then repeat the same thing for the second set of data. And then follow a very straightforward rule that essentially says that if the accuracy observed for this model is higher for, let's say, data from the second distribution, then it's more likely that the model was from the second distribution, which is expected because out of the two possible distributions, the one that it was actually trained on data from, it's more likely to be better performing on that. And we do have another variant of the black box test, which we term the threshold test, that involves another step for training a threshold and that performs slightly better than the last test. Here's a look at some of the results. So here we talk about experiments for the census and bone age datasets. The first one is essentially looking at different attributes for people and trying to predict their income group. And the second one looks at hand X-ray images and predicts the age group of a patient. And in these experimental settings, we set the first distribution such that the probability of female in these experiments is 0.5. So it's equally likely to be a female or not. And then for the second distribution, the same probability is set to alpha. And the alpha value is what we vary on the x-axis here. And what we see is the meta classifier, which is the white box attack, performs better than the black box attacks, understandably. And the second and more interesting point here is that the inferences seems to be different for different data sets. And there's quite some variation, as we'll see in the future slides. And that is what we propose the n-leak term for, and this is what we saw at the very beginning of the presentation. So what this essentially means is, if you look at a particular attack and the observed attack effectiveness, it's comparable to what the adversary could learn if it could directly sample n-leaked samples from the underlying distributions. So let's say an n-leaked value of 2 means that the adversary had the capability to sample 2 records from the underlying distribution, then the best performance that it could get is what you are seeing with the current attack. So naturally, a higher value of n leaked for the same setting means that the attack in that particular setting is leaking much more information. And what we see that even though for most experiments this number is less than 2, technically anything more than 0 is privacy leakage and the property is not intended to be leaked. And this metric is useful for comparison across different datasets, properties, and experimental settings. As a concrete example, consider this heat map where we, instead of varying just one of the distributions for the alpha values that you saw a couple slides ago, we vary both of them one at a time. And we plot those on the x and y axes. On the top right triangle, you see the distinguishing accuracy, and what we see is as the distributions become more divergent in the sense that the difference in their alpha values increases, the distinguishing accuracy also increases, which is expected. While in reality, the value of n leaked shows us that this is not the case for most cases. In fact, the extremes are what leak more information, and everything else has n leaked values of much less than 1 or 2. Now, all of the settings that we looked at in the experiment so far consider these different possible alpha values, and then we pick any 2 of them, and then we try to perform this binary kind of distinguishing task, which is useful to try and understand what the distribution inference risk is, but it's not very practical. The more practically useful setting would be one where the adversary could directly look at the models and predict what the alpha value would be. And we tried the setting for our datasets, and what we see here is that the inference risk for direct regression is much higher than classification. So for context, the dashed gray line here is what you would get for perfectly predicting. The x-axis is the actual alpha values for the models that we test on, and the y-axis is what the attacks predict. And what we see is that not only are the meta classifiers very successful, they don't overfit to the models that they see. So it's not the case that they only perform well on the ratios that they've seen in training. They also seem to generalize to ratios that they haven't seen in the training at all. And this is further evident when we look at the n-leak values for the regression case. So compared to the classification case where most values were less than 2, the values here can go as high as 270 in specific for the bone age dataset, which is quite high. There is still a lot of open questions in the field of distribution inference. First of all, there's no known good defenses right now, and even though there are good candidates like differential privacy and adversarial training which might work out, even though there's no theoretical reason for them to, our empirical experiments show that there's no hope for them and they actually don't seem to work in any of the cases. Next is trying to understand if there's any trade-offs with distribution inference and other kinds of inference, or even things like model generalization. And our initial experiments seem to suggest that protecting against distribution level inference attacks and membership level inference attacks might be at odds. And then further trying to understand how differences in training processes for these models can impact inference risk. In summary, machine learning models seem to leak unintended information about the training distributions, not just the training datasets as we have known so far. And the factors that affect this leakage are not very well understood. If you'd like to know more about our work, you can scan the QR code here, and here are the links to our paper and code base. Thank you.